So again, I'm Brad Chamberlain. I'm a principal engineer at Cray. And I'm going to be talking to you today about Chapel, which is a programming language that we're developing at Cray. Some of you may have heard about it before, some not. I'll both give an introduction to Chapel today for people who've never heard about it before, as well as an update on a few areas that are kind of new for those of you who know about the project but maybe haven't been following it closely. So as an introduction, again, I'm Brad Chamberlain. I got my PhD at the University of Washington, where I worked on a language called ZPL in the 90s. And there are aspects of ZPL that were carried forward to Chapel, but Chapel also tries to do much more than ZPL did. And I continue to be associated with UW Computer Science as an affiliate professor. But my main place I work is Cray. I'm a principal engineer there. I'm the technical lead of the Chapel project, which I'll be talking to you about today. And I've been working on Chapel since its inception, which is quite a while ago now. So if you're not familiar with Chapel, Chapel is a modern parallel programming language. It is designed to be portable and scalable, so you can run Chapel on these laptops, or a commodity cluster, or the cloud, or a Cray, or a supercomputer from another vendor. And the goal is, as we heard about in the previous talk, to have a single language in which you can do that initial prototype and put it together quickly and get your ideas running on your laptop, get it debugged, and then just recompile it on a supercomputer without rewriting it all in a new language. It's an open source project. It's hosted at GitHub. It's released under the Apache 2.0 license. And like any good open source project, it's collaborative. So we have a number of contributors from academia and industry outside of Cray. At the high level, you can think of the two main goals of the Chapel language as being to support general parallel programming. And by general, what I mean is if you have some parallel algorithm in your mind and some parallel hardware you'd like to run that on, you ought to be able to do that in Chapel. And if not, then we need to work harder on this goal. So it's not strictly for data parallelism or strictly for task parallelism or any specific niche. It's designed to be incredibly general purpose. And the other is to make parallel programming at scale much more productive than it is today. So to make it easier for people to write codes and read codes and maintain codes and port them and tune them. So this term productivity is used a lot with Chapel, but what I find when I talk to people is that productivity means very different things to different people. And so just to give some of the ideas of different notions of productivity that we hear, if we talk to young students or recent graduates, a lot of times for them being productive is a language that's kind of similar to what they're used to, which for a lot of young computational scientists are things like Python or MATLAB, or if you're coming from computer science, maybe something like Java. If we talk to people in the HPC community who've been maybe working their whole career in HPC, their attitude about productivity tends to be, well, that's that sugary stuff that I don't really need because I was born to suffer. Like, my job in life is just to grit my teeth and get through it. And this is kind of a tongue-in-cheek way of saying it. What they're really saying is they want full control because their job is to get all the performance out of these systems. And if they can't get that performance, then they're failing. And the common perception, particularly among HPC people, is that if your language is productive, then probably it's not going to perform well. And while that's often true in many cases, like I think object orientation is a good case where if you use lots and lots of deep object hierarchies, that can be counter to performance. We also believe that a well-designed language can have very productive features and yet permit the compiler to actually perform quite well. And I'll show you some examples of that a bit later on. And then if we talk to computational scientists, the astrophysicists or chemists or physicists who are trying to write these computations, usually their attitude about productivity is they'd like to be able to talk about their algorithm and their ideas and parallelism in that algorithm, but they don't typically want to wrestle with a lot of architecture-specific details. So they don't really want to deal with message passing or identifying CUDA kernels or things like that. They just want to sort of talk about, do this operation on all of these points in my grid or things like that. And so the Chapel language's definition of productivity is kind of a blend of these three things. We're trying to design a language which allows the computational scientists to express the computations that they want to without taking away that low-level control over performance that HPC programmers want, all implemented in a language that's as attractive as a recent graduate would like and would enjoy. Okay? So that's what productivity means to us. Now, a lot of times when you go around and you tell people you're working on languages, they sort of give you these kind of pitying looks like, well, why are you doing that? Because in addition to all the technical challenges of designing a language and implementing it, there are a lot of social challenges to designing languages, to getting people to use them, particularly when you are a new language and everyone wants to know, well, who else is using it, and am I going to be the only one? So this next slide is from a keynote that Kathy Yellick gave at our annual Chapel workshop last year. And she talked about why in HPC should we consider developing new languages. And she argues that languages have benefits for syntax, where they can help you write things more clearly and more elegantly and understand them better than if you use libraries or pragmas or things like that. That they can have semantic benefits, where the compiler can help keep you sane and avoid common mistakes by looking at the code and reasoning about it and preventing you from doing things that aren't good. Getting good performance, because the compiler can implement optimizations that maybe you wouldn't have the expertise or patience to optimize yourself as a programmer. And then algorithms, where the idea there is that a lot of times if you have a language that lets you express things more easily or more naturally than what you're used to, that can help you design new algorithms and optimize new algorithms sometimes much more efficiently than if you're doing it all in something much more low level. So these are Kathy Yellick's reasons for doing languages, and I saw this when I was just out of graduate school, and these are the reasons why I'm pursuing a language. So that's my answer to that question. So the outline of my talk today, I've just given you a little bit of context for Chapel and why we're doing it. Next, what I'm going to do is talk a little bit about Chapel and productivity, show you some simple examples of benchmarks and how they compare against the status quo. Then I'll give you a very quick tour of Chapel just so that you leave with a little bit of an idea of what the language looks like. And then the third part of my talk will be talking about CUDA, which is a system that one of our users has developed recently, which allows them to basically write code that looks like NumPy code in Python and Jupyter. And yet it's implemented using Chapel. And so their users sort of think, well, I'm just writing normal Python code, but then it's executing on a supercomputer and scaling to much bigger and faster speeds than they could get otherwise. And then, of course, I'll summarize at the end. So when we compare Chapel to other languages, there are a lot of themes in other languages that we've tried to capture in Chapel. And so you can view Chapel as sort of trying to be the best of several different worlds. And so the first theme is programmability. And again, I think that's an area where I think we suffer a lot in HPC. I don't think we have really great ways to write code clearly and cleanly and make it easy to support and port and maintain over time. And there our goal is to be as programmable as Python, because more and more when you talk to young programmers, Python is the thing that they find most natural and most comfortable and easiest to use. And we'd like to be a similar language in that respect. At the same time, Python doesn't typically result in great performance because it's a scripting language, it's dynamically typed. So our goal is to have the programmability of Python and yet generate code that's as fast from a scalar perspective as, say, a Fortran is, which still a lot of people consider sort of, one of the fastest languages there is. We want to be as scalable as MPI or SHMEM or UPC if you use those, as portable as C, as flexible as C++. And by that I mean the ability to do things like define your own data types and your own operators and do overloading and things like that. And then this last theme here is to be as fun as your favorite programming language. And this is another area where in HPC people often sort of giggle like, well, programming's not supposed to be fun. But a lot of us, when we got started programming, we did it because we really enjoyed programming. We found it enjoyable and fun and a fun puzzle and a fun exercise. But it's very rare that I find people in the HPC community who feel that way about programming MPI or CUDA or things like that. And I think this is one of the reasons that HPC has a challenging time both attracting young graduates and then retaining them, is that I think you could go program in a number of modern languages at a number of companies. Why would I want to come to HPC and program in C and C++ and Fortran and MPI? It just seems very old-fashioned to a lot of people, I think. So our goal is to return some of the fun of programming to the HPC community. And to demonstrate some of these themes, I'll look at a couple of very simple benchmarks. These are designed to just give you a flavor of where we are with performance and a little bit about Chapel. They're obviously very simple benchmarks, but the goal is to have something that I can put into this talk without taking up all the time. So the first is pretty much the simplest parallel benchmark you could think of, stream triad. If you're not familiar with it, it's fairly simple. You take a vector C, multiply it by a scalar alpha, add it to a vector B, assign it to another vector A. And because we're all parallel programmers, we know that this is a computation that's very trivial to parallelize. If we're running on a multi-core system, we could just chunk our vector up into a number of chunks and have each distinct core or task do the computation across its subset of the chunks. If I go to distributed memory, I can do the same kind of thing, but here I'm typically going to replicate alpha so that each compute node has its own copy of alpha and doesn't have to communicate with the others. And of course, on most modern machines, we're dealing with hybrids where you have both shared memory and distributed memory because we have multi-core compute nodes. So this is, again, a very simple computation, not designed to be anything super fancy or complicated. And if we look at this and how it's written in C plus MPI, the code ends up looking something like this. This is the reference version from the HPC Challenge benchmark suite. And if you can see the colors, the red code is MPI. And there's not very much MPI in this because we just have to do setup and teardown, and there's no communication during the computation itself. The actual kernel is this green loop here, and the rest of it is just kind of C boilerplate for allocating arrays and freeing arrays and things like that. Now, if we want to get that hybrid code, we can also mix in some Openmp, which I'm showing here in blue. So I can annotate my loops and say these loops are parallel, and then I'll get multi-core parallelism in there as well. And this is not a very complicated code. Probably most of us could write it pretty easily. If we look at how this is written in Chapel, this is the computation here. I haven't really left any code out except for a couple of small expressions I'll get to in a second. And you can see it's much shorter and sweeter, and I would hope simpler to understand than the MPI, even if you aren't already a Chapel programmer. But what's nice is not just that this is a nice short code, but it's also very flexible. Depending on those two expressions I left out and how I compile it, I could run this as a serial computation, a shared memory or distributed memory computation, the hybrid that we talked about, or any other kind of way of mapping the computation down to the system that I can come up with. And the sort of secret sauce there is this expression that I've sort of left out a little bit of detail on. And basically what you can do is plug different recipes in there and say, here's how I'd like to map these indices and the arrays over them and the computations over them down to my system. And by plugging in different recipes there, you can come up with very different implementations of this computation without changing the actual science, if you will. Not that there's much science going on here, but the actual computation on the array stays the same. It's just a few changes in the declarations which say, how do you want to map this down to your system, and how do you want it to run? Okay? So it's a short code, it's a flexible code, and it's also a code that performs well. This is a performance graph going up to 256 compute nodes, 36 cores per node. So this ends up being about 9,000 cores out here at the end. And this is a performance graph, so higher is better. And the reference MPI plus Openmp I showed you is in green, the Chapel's in blue. As you can see in the graph as I've shown it here, the Chapel is slightly behind the MPI plus Openmp, but that difference is pretty, it's not a very deep difference. What we did here is we ran the MPI code with no huge pages module loaded, and the Chapel code with huge pages modules. Because that's the mode in which each typically prefers to run. But this is a code that doesn't benefit from huge pages at all, so Chapel takes a little bit of a hit there. If we were to swap the huge pages module for either one of these, the lines would match up. So we've just tried to be as fair as possible to to MPI essentially, but we could get Chapel to compete identically if we just unloaded the huge pages module. So again, simpler code, but one that's competing pretty much identically with MPI and Openmp. So let me go now to a slightly more interesting computation, although still a very simple one. This is the random access benchmark. If you're not familiar with it, you have a 1D distributed table, and then you're basically doing a number of computations against that table at random simultaneously. So just kind of randomly updating various elements across the table, across distributed memory. And of course, as you're doing this, because everyone's independently computing random updates, sometimes those updates may conflict with one another, as in that gold box up there. And so then you have to decide whether you're going to write a lossless version of this algorithm in which none of the updates can be lost, or a lossy one in which you might permit some of these to be dropped on the floor, and maybe that doesn't affect your algorithm. And for today, I'm going to focus on the lossless algorithm because I think it's slightly more interesting. So again, this is the reference version of the implementation in MPI. You can see there's more code here, and in particular more MPI code in red than there was in Stream. That's not surprising. It's a slightly more complicated benchmark. There has to be communication in order to communicate all of these updates across the node. And I think what's interesting about this code is if you zoom in on the top up there, this is a comment that basically says, these 3 columns of code are basically doing this update to this table. Right? So let me explain to you what all this MPI code is doing with this small comment. And then if we look at the Chapel kernel for this computation, the computation itself in Chapel is about the same size as that comment. We're basically saying, for all of the updates we need to do and the random values that we're generating, index into the table based on the random value and XOR the value in. And that's pretty much the whole computation in Chapel. So, again, about as succinct as the comment for the MPI code. So this is a case where not only are we also succinct like we saw in the previous stream benchmark, but this is a case where we actually perform much better than the reference version as well. So again, a performance graph where higher is better, again out to about 9,000 cores. And here the Chapel code is scaling really nicely in blue, whereas the MPI code is dropping off here in green. And the reason for this is that the Chapel code expresses the computation very cleanly and gives the compiler a lot of leverage in terms of how it maps down to the architecture. And so specifically, when the compiler sees this loop, a for all loop in Chapel typically says, have each of the cores doing a number of serial updates. But then in addition, the for all says, and all the iterations here can be done in any order. So the compiler can look at this and say, well, I know I'm targeting a Cray, so I've got atomic operations in the network. So I'm going to map these to the atomic operations in the network. And then I see it's within a for all loop, so I can do these operations in any order I want. I can just fire them all off and then sort of fence at the end of the loop to make sure that they're all done. And as a result of that, the Chapel performance can just scale really, really well, about as well as the hardware can itself. And I don't mean to imply that you couldn't make an MPI version that competed with the Chapel. We're just generating C code, so you could write the exact same C code our compiler did. But the point is, this is how much work it was to do the basic reference version. How much more work would it be for you to get that same performance? Or to put it another way, if you were to feed this code into the compiler, would a compiler ever have any chance of doing a similar optimization in order to get the same performance we do with the Chapel? And as a compiler person, I would argue that no, there's no way that a compiler is going to look at this code and say, oh, I can just implement something as simple as what I did in the Chapel case. So I said at the beginning of my talk, I think a lot of times people think productivity is counter to performance, but I would argue in cases like this, if you express something very cleanly to the compiler, you give the compiler a lot of leverage to do optimizations and to get it to perform potentially even better than most humans could do. So returning to Kathy Yellick's slides, this is an example that shows that both the syntax is very nice here because it allows us to express the computation much more succinctly, but also it gives us this performance leverage because we've expressed the computation very directly to the compiler and allow the compiler to do a lot of optimization on our behalf that we might not be willing to do ourselves. Okay? So again, I've just shown you two very, very simple types of computation, embarrassingly or pleasingly parallel, stream triad, and then these global random updates. These are obviously very trivial benchmarks, but the kinds of patterns we're seeing here about short codes and performing well are things we see across a number of different computational styles, including local loops, bucket exchange patterns, stencils. And if I had more time, I could walk you through all of these results. But the main point here is that, generally speaking, Chapel does well across a wide variety of computational styles and is generally matching or beating reference versions more and more as time goes on. Okay? So with that, I'm going to transition to giving you a brief introduction to Chapel. I think there's nothing more frustrating than going to a language talk and leaving going like, well, that sounded nice, but I have no idea what the language is actually like. So I'm going to teach you a little tiny bit about Chapel, and I'm going to pause and have some water. And I meant to say at the beginning, I'm happy to take questions as we go if you'd like. There's no reason to wait till the end if you have any questions. Yes?
I guess, this is probably going to answer better in your slides. You showed some programs and you showed how they can be mapped to the hardware. Like, to what extent does the user have to actually understand that mapping to use Chapel? Because, it's productive, but the terms that you explained it in are low-level C, C++, HPC terms.
Right.
And so, I realize that we're that suffering audience.
Right.
But what is how much does the user have to know about that?
Right, so to summarize the question for the recording, the question was kind of, this sort of looks nice, but how much does the user have to know about sort of what's actually going on and how it's being mapped down to the system in order to use Chapel effectively? And I think that's a really fair point. I would say that we're at a point now in Chapel's evolution where those of us who work on Chapel daily are pretty good at sort of knowing what happens and understanding how to write the code in a way that maps down well to the system and compiles well. And I think we're not far enough along in terms of our compiler being really great or our tools being really great, such that often many other users kind of try something, it doesn't work that well, and we have to work with them pretty closely to get it perform better. I think that's something that will improve over time, but I think just kind of where we are today, it often does help to know what's going on. And I'll also say that it's also the case that it can depend a lot on what kind of hardware you're running on today. So for example, we work for Cray, we focus predominantly on Cray and making sure that we take advantage of Cray-specific features. And a lot of times we have users who are trying to run on an InfiniBand cluster or something like that, which we support and it works there, but we haven't spent as much time getting the performance as optimized there. And so that can also cause a problem where the case we focused on isn't always the one that users care about. And so that can be another kind of mismatch. But I think you're right. One of the things that our users often ask for is kind of like a performance programmer's guide to Chapel. Sort of, if I'm approaching Chapel with a specific problem, what should I be thinking about? What kind of patterns should I be looking for or avoiding? And that's something we have a lot of knowledge within our group about, but haven't done a good job of disseminating that to other people yet, if that makes sense. Yeah, it's a good question. Thanks. Okay, so as I said, the next thing I'm going to do is give you a quick introduction to Chapel and some of its features. When I talk about the language, I tend to talk about it in terms of these different areas of the language. And so I'll take a few of these at a time as I go through this. I'll start with what we call lower level Chapel, although I hope when you see it, you'll still find it very high level. And I'll start specifically with the base language, which you can think of as if I took Chapel and I pulled out all of the features that related to parallelism or scalability, the base language is what you'd be left with. So think of it as like the C or the Fortran on which Chapel's based, except that we started from scratch rather than basing it on any specific language. And the other thing I'll say is that each of these examples I'll show you is itself a complete Chapel program. So you could type it into your editor, compile it, and run it. I'm not sort of leaving out much boilerplate code or any boilerplate code for that matter. And so for the base language to illustrate, I'm just going to give you a very simple Fibonacci iterator example. The idea is that I'm basically going to feed in some value n and print out that many Fibonacci numbers. And so over here is a Fibonacci iterator I've written, and over here is the code that uses it and drives it. I start out by declaring what we call a configuration constant in Chapel. This is a constant like in C, so I say n is given the value 10. But this keyword config basically gives you the ability to reset its value on the command line. So if I've declared n in this way, when I run my program, I could say -- n equals 1,000,000, and that'll override the default value of 10. And so this is sort of a way of just changing configuration parameters on a run-by-run basis without having to do a lot of argument parsing yourself. So fairly sugary feature, but one that once you start using it, you're happy never have to deal with argv and argc again, for example. You can see we have iterators in the language, which are a lot like functions, but rather than returning once, they have this yield statement, which essentially says, kick this value back to the call site, but then continue executing from that point. And so we invoke the iterator here. I say for f in fib of n. And so each time this yields a value, that's going to come back here to f, and then I print it out, and then I continue and continue running until eventually I fall out of this routine, and then we're done with the loop. So you may have seen iterators that the way we do them is pretty different than like traditional C++ or Java iterators, but they may be more what you're familiar to from scripting languages like Ruby or Python or things like that. You'll notice in my code that I haven't declared the types of anything. So variables like n or I or current or next don't have any type information. This doesn't mean that they don't have types, so it just means the compiler is figuring out the types for you. So for example, it knows that 10 is an integer, so therefore it knows that n must be an integer. And then when it passes n to fib, it says, well, this n over here must also be an integer, and current and next are integers, so I'm yielding integers, so f must be an integer. And it just propagates this type information through the code, again, statically, so that we're not paying any execution time overhead for that. Now, you can also write Chapel in a mode where you explicitly specify all the types, and sometimes this is useful if you're creating a library interface, for example, or you just want to document your code more. So here, for example, I've shown that everything is integers. But in my slides, I'll typically leave the types off just to keep the code a little bit simpler and shorter, and also to show off the feature a bit. Yeah? The typing is all figured out at compile time, yeah. And so specifically, like in a scripting language, something might start out as an integer and then later become a string or something like that. Because we're a statically typed language, because performance matters to us, that's not the case, right? So once the compiler figures out n is an integer, it's an integer forever, basically. Yeah. Here I'm just iterating over the fib iterator by itself. We also support zippered iteration in Chapel, in which you can iterate over multiple things simultaneously. So here I'm iterating over the values 0 through n minus 1 and fib of n, and then I'm using that to make my output look a little bit nicer. We also support parallel iteration over multiple collections, and that's used a lot once we get into the parallel features. We have range types and operators in the language, which just represent an integer sequence. So these are the integers 1 through n. This basically says start counting from 0, count to infinity, but don't only give me the first n things. So this is kind of a stylized way of writing 0 to n minus 1, for example. Yep.
So with stuff like zip,
Yep.
like in a typical language that would create an object, right? But you said zippered iteration. So does that mean that like there's special support for zip to make it efficient, or what's?
Yeah, there is. So in the most general case, we do have a fallback implementation that creates two objects and sort of grabs a value from each and sort of zippers them together. But more typically, what our compiler is going to do is to look at the iterators and basically figure out how to merge them together into a single loop nest. That said, some of the cases where we don't have the performance we need today are cases where this zippering doesn't work out so well. So this is an area that works well, particularly for 1D loops currently, but once you get to multidimensional things, sometimes multidimensional parallel zipperings tend to fall off a bit of a performance cliff. So that's ongoing work to make that better. But the language has, in addition to this kind of serial iterator we're seeing here, the language has a number of different kinds of iterators, including parallel iterators and what we call leader-follower iterators. And those are all designed to support things like this zippered semantics in an efficient way that makes sense in parallel without kind of ending up with non-deterministic results. We've got some papers about that I can point you to if you're interested in that topic. So we also have tuples in the language. So for example, when I do this zippered iteration, the values that are yielded for each of those things I can store in a tuple and refer to them as I and F. We also use these to do multidimensional array indexing and to write rank-independent codes. So that's the base language, just a few of the key features. The base language is very, very large. So we wanted sort of anything you might expect from a modern parallel programming language, or sorry, a modern programming language. So we have object orientation and memory management types and nillable versus non-nillable types, generic programming error handling. It's sort of a huge base language, which is not unusual for modern languages. But there's a lot more to it that I'm going to be able to tell you about today. So this is just sort of a list of other things so that you know there's more there. If, for example, you're like, well, where are my objects? I need objects, for example. But let me get to the things that are a bit more unique about Chapel. I'm going to go to task parallelism and locality control next. So task parallelism is about saying what should run concurrently with other things. And locality control is about saying where should things run, which is particularly important on distributed memory systems, of course. And I'll do both these examples with a single example. But let me define one term before I get there, which is the notion of a locale. You may have seen this on some of the graphs I showed earlier. In Chapel, a locale is basically a unit of the architecture that can run code and store variables. And typically, if you think of a locale as being a compute node, that's a pretty good mapping for the definition. And when you run a Chapel program, you specify the number of locales on the command line. So here, for example, I'm saying, give me 4 locales. That will cause it to go out and talk to Slurm or QSub or whatever you use and get those resources and start running your program. And then within the program itself, you have this built-in array of locales that refers to the resources on which you're running. And your sort of, the entry point to your program, your main, if you will, always starts running on locale 0. Okay, so let's look at some code. This is basically a parallel hello world example. I'm going to start by querying this variable called here. And this is a way of referring to the locale on which your code is currently running. And so at the top here, I say here.numpus, or number of processing units. And this says, for the compute node I'm running on, how many cores do I have available? And so if I'm on a 16-core system, for example, num tasks would be set to 16. Or if it's a 2-core system, like I've shown here, num tasks would be 2. Then I use this co-for-all loop, which is a high-level way of introducing tasks into Chapel. So like the for loop we saw before, this is basically invoking an iterator, or in this case, iterating over a range. But each iteration is going to be executed by a different task. So if I have num task, or in this case, I'm iterating from 1 to num tasks. So again, if I had 16 cores, num tasks is 16. I'll have 16 iterations of this loop, each of which will be a completely distinct task running its own copy of the loop body. So in my example here, because I didn't have much space, I just made it a 2-core system. And so if I ran this, I'd get 2 little hello world messages printed out. And because these are independent tasks and they're not at all synchronized, those messages could come out in either order. And so you can see, for example, in this run, task 2 happened to complete before task 1 did. Yeah?
You mentioned before that for all doesn't have any order either, so how does go for all different?
That's a good question. Let me come back to that. I'm going to get to for all on a slide, but there's a subtle distinction between them, but you're right, yeah. They're both parallel loops. This one, though, is very explicit. It literally says every single iteration is a separate task. Now, as I've written this code here, this is just a shared memory program. I haven't done anything to talk about any locales, and as I said, I start running on locale 0. So if I just ran this code, it's never going to leave locale 0. It's just completely shared memory. But with a minor change to it, I can basically make it distributed memory. So what I've done here is I've referred to that locales array I mentioned. And again, this is an array that represents all of the compute nodes on which I'm running. And I'm going to use a second coforall to basically create one task per compute node, or one task per element in that array. And then I use this on clause here, which is a way of saying where should things run. And so this is going to have each of those tasks I create run on the locale that it corresponds with. So at this point, I sort of have SPMD parallelism. I've created a number of tasks equal to my number of compute nodes, and I've told each task to run on its corresponding compute node. And then each task is just going to run the inner loop as we saw before, query how many cores are on that compute node, and then do a nested coforall to create a number of tasks equal to that number of cores, and print out its message. So with those small changes to the top of the program there, I basically changed it from a shared memory code to a distributed memory code, and I'm basically printing out a message for every core across my entire Cray or whatever I'm running on. Okay? So that's task parallelism in a nutshell. There are a few other features I didn't get to here. So we have atomic and synchronized variables, which are ways to have tasks coordinate with one another and synchronize with one another. These aren't kind of completely independent tasks, but you can have, for example, producer-consumer relationships between them. And then there are a couple of other ways to create task parallelism, begins and co-begins. But by and large, you've seen sort of a lot of the features for the task parallel section of the language. And so now I'm going to jump up to what we call the higher level features in Chapel. Those low level features were very explicit and about, create this many tasks and run them here. And these higher level features are a way to express parallelism much more abstractly, and where we hope many users will be able to work. So again, a very simple example. Another case, you could type into an editor and just compile. So this is a whole program. And basically here, I'm just going to create a two-dimensional array and then just initialize it in parallel, essentially. So after I declare my problem size n, I declare what we call a domain, this domain D. A domain is basically a language level concept for an index set. So I'm saying that D represents the indices 1 through n, 1 through n. So it's like a two-dimensional index space. And you can think of it as being like an array, except that I haven't actually allocated any data other than what I need to store the bounds of the domain. I can then declare arrays over that domain. So here I'm saying, give me a variable A whose indices are defined by D. So A is going to be an n squared matrix, essentially. And in this case, I say that the elements should be reals. They should be floating point elements, essentially. And so then I'm going to use a for all loop. And so let me come back to the question about how do for all and co for all differ. So with a co for all loop, we're literally going to create a task for every single iteration in the loop. But here, if I was running over 1 million array elements, for example, I probably don't want to create 1 million tasks to do that, unless I happen to have 1 million cores. And so what the for all does is say, create an amount of parallelism that's appropriate for the thing you're iterating over, and then divide up those iterations between those tasks. So for example, if I was running this on a 4-core system, probably what would happen with the for all is I'd get 4 tasks, each of which would take a quarter of these million elements and just iterate through those serially. Okay, so the for alls are sort of a way to have, to defer how much parallelism is created, not specified explicitly, but to defer it to the thing you're iterating over. So in this case, for example, D is the thing that controls how many tasks do I get, how do they divide up the iteration space, and so on. And then basically I'm just iterating over all those indices and setting A to be a simple function, the row and column indices. So I end up with an output like this, for example. Now again, this is an example of a program that's shared memory. I haven't done anything explicitly to talk about locales, nor is there anything implicitly referring to other locales. But again, with a small change, I can basically use the DMAP concept we saw at the beginning of the talk and say, well, here's how I'd like you to map these indices down to my locales. And so, for example, I could use the cyclic domain map, which says just deal them out round robin across the locales. And with that change, I've changed this from a shared memory code to a distributed memory code. And so now when I run on 4 locales, it'll divide up the indices and the arrays and the iterations across those locales and across their cores. But again, I haven't had to change in the actual computation here. All I've had to do is change the declaration of that domain. And that's affected the arrays and the loops over those domains and arrays. Okay? So this is your quick example to data parallelism in Chapel. There are a lot of other features for data parallelism, a lot of features around slicing and different kinds of operations you would want to do on arrays, the kinds of things you'd expect from a good array language. And I should say, in addition to the dense multidimensional arrays we saw in this simple example, we also have strided arrays, sparse arrays, and associative arrays. So you can use these data parallel features with a number of kind of irregular or strangely indexed sets of data. And at this point, going back to the beginning of my talk, you sort of know what you need to know to understand a lot of the code you saw in the stream triad example and in the HPCC random access example. 5 minutes? Okay. And so that's your quick tour of Chapel. If you want to know more, we're happy to do tutorials for people online or to visit you or things like that. We also have a number of online support channels I'll talk about at the end of the talk briefly. I'm going to hold the question because I'm running short on time.
Maybe just yes or no.
Okay.
Does this work with GPUs?
Does it work with GPUs? So there has been academic work that has gotten Chapel working on GPUs. If you download the official release today, there is not GPU support. That's something we're working towards still, but none of that work has ever become mature enough yet that it's made it onto master. I'll mention that we have an LLVM-based backend, and so our strategy for targeting GPUs is to make use of vendor-provided LLVM backends and use that in order to get to the GPUs. Okay?
Yes, please, a question.
Okay.
Can you interact with C code? For example, if I
Yes.
write a kernel in C?
Yeah. So the question was, can you interact with C code? And you can. You can both call from Chapel out to C, and you can also call from C into Chapel. And actually, that's a great transition to this next section. So as I mentioned at the top, this is a case that a user did recently called Arcuda. Imagine that you've got a bunch of Python programmers and some HPC problems you want to solve, and HPC systems to solve those problems on. The question is, how are you going to use those Python programmers to effectively use your HPC systems? Because Python doesn't tend to scale and perform really well on HPC systems. And so what this user did was develop Python libraries that are actually implemented under the covers in Chapel. That's a lot like what most Python libraries do. A lot of the fastest ones are implemented in C. But here, instead of going to C, they go to Chapel. And so in addition to performance, they're getting the parallelism and scalability that Chapel gives them. And what they're doing is they're basically creating a library that looks exactly like NumPy in order to make it trivial for a user to start using the library without becoming a Chapel expert. So this is a screenshot of them running this Arcuda library from within Jupyter. And I'm not actually a Python expert myself, but essentially they're creating some arrays here and then doing things like adding them together and computing a reduction over them and so on. But under the covers, that's being distributed out to their large-scale systems and executing over terabytes of memory. But to the user, it looks just like normal NumPy code. And that's very attractive, again, because their users are NumPy authors. They're not HPC programmers. So by taking this approach, this user was able to interact with a distributed running Chapel program running within Jupyter. So they were on Jupyter on a front end. The Chapel was out in the back end running across their HPC. They were talking to each other using ZMQ. They could run that same back-end server program on a Cray, on an HPE, on an InfiniBand, on a Mac. So again, this gets to the portability point I made at the beginning of my talk, and allowed them to sort of develop it locally and then deploy it on their larger systems. They could compute on terabyte-sized arrays in seconds. I think the record that they've done here is like 32 terabytes of arrays on some of their demonstration codes. And they did all of this in about 1 month of effort, which I think is a testament to Chapel's productivity. And I would say most of the effort was related to getting the client and server to talk to each other and dealing with kind of the dynamic type to static type mismatches between Python and Chapel, as opposed to anything related to the array computations themselves. So when we asked them, why did you do this in Chapel? They said, well, it's a high-level language. It made for a lot less code. It had great array support, good support for distributed arrays and synchronized and atomic variables. It's a language that's close to Pythonic, so if their scientists want to go under the hood and sort of play around with the underlying implementation themselves, it's a nice gateway language for them to learn. It's portable and scalable, and we saw that in their results. They used the quote, we can go from Raspberry Pi to Cray XC without changing the code, and that's very attractive to them. And as you just asked, it integrates with distributed numerical libraries, so they can make use of things like FFTW or FFTW MPI without re-implementing all that from scratch. Okay, so I'm out of time. So to summarize real quick, I think Chapel's a language that cleanly and orthogonally supports expressing parallelism and locality in a way that's independent of the architecture, but in a way that still allows you to say how to map that down to the system, how to map your computation, your arrays, your iteration spaces down to the system in a way that still lets you reason about and control about performance and locality. It's a powerful language. As we've seen, it supports very succinct, straightforward code, and it can result in performance that competes with, or as we saw in the RA example, sometimes beats traditional techniques like C plus MPI plus Openmp. And as we've seen through the Arcuda example, it's attractive to Python programmers, both in the sense that it's sort of similarly high level and so attractive if you're reading and writing Chapel code, but it's also attractive in an interoperability sense for writing Python libraries and never even having to touch Chapel, but still benefiting from it. And the rest of my slides are basically pointing to resources like our website, our documentation, various online community sources like Stack Overflow, Gitter, GitHub, where we interact with the community, social media channels, things you might want to read. And these slides will all be available online. So if you want to sort of get these resources, don't worry. Like, these slides will be on our website, and I'm sure they'll be on the HPC Now website as well. And last thing I want to mention is if any of you will happen to be at PLDI or FCRC next week, we have an annual Chapel workshop that's taking place there. We'll have a great keynote from Anshu Dubey from Argonne, and we'd love to see you at the workshop if you're going to be there. So thanks very much, and that's my talk.
Thank you so much. I believe we have still time for a couple of questions, if you want.
So how has the uptake been so far on Chapel? Are there any big scientific applications out there, open source, available to everyone to use that use Chapel underneath? Or?
Yeah, so the question is sort of how is Chapel's adoption going? And I would say that it's all going in the right direction, but it's a slow process. And this gets back to what I mentioned at the beginning of the talk about it's very challenging to get people using a new language because they're terrified of being the only one to use it, and what if the language goes away? All completely reasonable reactions to have. So one of my favorite examples was there were some students from Montreal who were doing computational fluid dynamics codes, and they sort of came with this exact same question about 6 months ago and said, hey, we saw Chapel, we tried writing some codes in it, they worked really well, we're really excited about it, but our advisor is really nervous about letting us do our research in Chapel because he's worried about, is anybody else using it? Is it going to take off? And we sort of told them that, yes, other people are using it, but not a ton, but somebody needs to be those first users. And they end up using it, but they're among a sort of a community of maybe like a dozen sort of active Chapel users. I would say that most people who have used it so far tend to be academics, people who are more interested in sort of exploring scientific ideas than writing million-line, long-lived HPC codes. This Arcuda example that I mentioned is, I think, one of the larger codes. It's not quite open sourced yet, but they're working it through that process, and I believe it should be open sourced by the end of the month, as I understand it. And that's getting close to about 10,000 lines of code currently. Lines of code is also interesting with Chapel because, of course, 10,000 lines of Chapel code can often be lots more C plus MPI code. Who else do I want to mention? There's an astrophysicist at Yale who's been using it for many, many years now, and he's sort of the time to science type of guy that I have mentioned. Pacific Northwest National Labs has been using it for creating a graph library, and so they're one of our bigger users lately. We're using it internally at Cray as well for developing some new AI software, and so we have a hyperparameter optimization package that we've recently started shipping that's developed in Chapel. So the community is sort of small but trending in the right direction. The other thing I'll say is that while we've been working on Chapel for a long time, it's only in the last year or two that we've really started telling users, like, yeah, we think it's ready for you. For most of Chapel's development, we've said, I wouldn't write my next code in it, but what we'd like you to do is try it and give us feedback. And that feedback has been really valuable for making the language better and better. And as the performance has really started to come online in these last couple of years, and the features are starting to gel, now we're at the point where we're really trying to encourage people to use it more. Whereas again, for most of the 15 or so years I've been working on it, we've told people like, no, you probably shouldn't use it yet, but hopefully someday. And I think that day more and more is now.
So you were there from the very start? It's about 15 years old, or?
Yeah.
You started the project, or?
Yeah.
Yeah. Okay.
Yeah. I mean, there was a team of us, so I don't want to take full credit, but I was the person who, so there's a program called High Productivity Computing Systems run by DARPA, where the goal was to make things 10 times more productive. And I was the person who said, I think programming languages are an area where in HPC we're not making people productive at all. I think we should invest here. And the first time I said that, Cray's executives were like, no, we're not going to do that. That's crazy. And then we talked about it some more, and eventually they said, oh, okay, you've got a good point. Let's do it. And so that's kind of how it started, yeah. Todd?
How do HPE's executives feel about Chapel?
I have not had a chance to talk to HPE's executives about how they feel about Chapel, so I cannot answer that. I will say that, not speaking for HPE directly, but in general, we've tried to create industrial partners around Chapel, and unfortunately, the reaction has been very much the same as from anybody like, languages are hard, that seems really scary, we're nervous about investing anything there until we know it's going to be a sure thing. And the trouble is, you never know a language is going to be a sure thing, so you either have to do what I've kind of done for my career, which is just say, look, somebody needs to be creating better parallel language than we have today, and I'm willing to be one of those people. Or you just have to kind of be a chicken and hope somebody else does it. And so far, we haven't found many people who are willing to become partners outside of like academia, for example.
What percent of your external users are contributors to the language
So-
itself?
Yeah, so the question there for the recording is, what percentage of the external users are also contributors? I would say the number of, a lot of them are, but most of the external users tend to contribute more in the area of libraries than in the language or compiler implementation, which is actually completely appropriate, because one of the things we found was maybe like 3 or 4 years ago, we were like, okay, the language is starting to come together. We started to shop around to users a bit more. And the main thing we heard is, nowadays people don't really, to be kind of snide about it, they don't really write code anymore. They just take things from libraries and cobble it all together into an application, right? People use Python sort of like Google, like, what calls do I want to make? And then they grab things from other libraries. So we got to the point where we created a great language, but we didn't really have the library ecosystem that people expect from like a Java, Python, C++. And so where our users have been really great is they've said things like, well, I want an FFTW library, and then they've gone and created it themselves. Or I want an MPI library, and they've gone and created it themselves and contributed it back. So I would say most of our users do contribute code back, but usually in the form of libraries. Most of the core compiling runtime work is still done within our team at Cray.
Okay, we are running out of time. I think that there are a lot of conversations and discussions about this and many other things. Chapel is really good for training as well. So it's something that links a little bit with HPC Nepal that we talked yesterday. But we can talk about all those things in the wrap-up session later today. So we have room for discussion all those things. So coffee break is ready, and we have a short time because then there's another talk, and then we have to run to the DPSC. Okay, so thank you so much.
I've got stickers.